go live and okay.
Very good. Let's see. Let's do.
Okay, we are ready.
Okay, great. I'm just getting the right thing to share. Oh, there it is. Excellent. All right, share that. Now, if I'm correct, y'all can only see this. Oh no, I don't. Did I mess up the share? Let me see if I can. Okay, so if I move that, it messes it up. Okay, I'll keep it over here. That's fine. Let me spread out your heads. Now with this lecture today, I do want you guys to feel free to interject questions in the middle like we normally do, just so you know. And I want to explain, I will catch up the repo. I just felt in a dilemma. Pact asked us not to share certain things completely that we would put in the book repo, but I'm beginning to think that we're okay. I want to show y'all feature conditioning today, and this deals a lot with scaling, but a little bit with encoding. And so if we go to ways to encode text to numbers, the two most common ways we do it in basic machine learning, and I mean basic, we're not getting into natural language processing, is one-hot encoding, where, for example, let's say we had a feature that just had colors, red, green, or blue. So I use this fake data technique here to random sample from colors one at a time. Because it returns an array, I just take the 0th element because I just want an array of these color names for I in range 15. So this is just going to basically give me a random array of those 3 colors. Now, what I want to do is do one-hot encoding, but I'm just going to use my own code first, pure Python, to do this. So I've got my word features, I've recreated them again, and now I'm pretending that I received these. I didn't create them. So I'm finding out, okay, I'm going to do a set. Set gives you the unique values of an array. I'm going to turn it back to a list. Now, and I want y'all to feel free to ask me questions here. These are Python tricks. I'm going to go for each color in this array of word features. And let me show, there's that array of word features or something similar to it. I'm going to say 1 equals integer of color equals colors 0. And 2 equals integer of equals colors 1. Now what's happening here? Remember, I got my unique set here. So if the color that I'm looking at in this array, that I'm pulling from this array, equals the color, the first colors in my color set, my unique colors list, I will set that value for 1. So this is going to be 0 or 1. I do the same thing for number 2. I'm just assigning these, and that will be 0 or 1. But why aren't I doing it for a third potential color? Well, let me show that real quick. Let's see. Just to show y'all this picture, when I'm doing, I've shown y'all this before, I'm pretty sure, when I do one-hot encoding, if I'm taking this red, blue, and green, etc., when I see that red and blue are both 0, that implies green is present. So if I have 3 things that I'm one-hot encoding, I only need 2 of them. If I have 9 things I'm one-hot encoding, I only need 8 of them. Because again, there's going to be a case where they're all 0, and that implies the last one is 1. Okay, so we'll go back to this. Oh, were y'all able to see that when I changed tabs?
I was, so.
Okay, okay, thank you, Jonathan. So that's why I'm not doing a third one. Now I append this list of 1 and 2 to encoded, this empty array that I made. And then I print colors. Again, I'm leaving off the very last one in this case, and I get blue, red. And again, when they're both 0, that implies green. So there we have the greens. So that's one hot encoding. This is just another example where I repeat that, but with NumPy. And what's unique here? Okay, I still have these colors. I use this same technique to create fake data from them, from these colors. I've got the array, but now what I'm doing is I'm turning it into a NumPy array. And I'm reshaping it so it's a column. In other words, it's an n by 1 matrix, essentially. And then I report the shape. Well, no, excuse me. I capture the shape. Now I use, instead of, notice what we did here, we're pretending we didn't create the fake data. Now we're getting the unique values with Python, pure Python here. But down here, I'm using the NumPy technique of saying unique, np.unique. And that's how we get those unique colors. Now I'm doing roughly the same thing, but first I create a temp of zeros and the shape. That's going to give me a column matrix. And then I say the word feed. This is how NumPy can be so slick. As I go through each of those unique colors, I'm saying this new array, this new n by 1, it's going to be 15 by 1 to be precise, column is, now I hope everybody understands this NumPy notation now. This means every row, the first column, but again, we only have one column because we took the shape. And then we're currently this reshape that we did, excuse me. So that is the 15 by 1 right there. And that's what we assigned here. We kept it as a steady variable. But it's saying for this new array, everywhere where word features, which is now a column because of up here, equals the current color, set it to 1. Everything else will still be 0. And then we're building up new word features. We're adding to the existing word features, and we're saying NumPy horizontally stack these individual matrices that are 15 by 1 matrices, and we're stacking the existing word features column matrix to and putting the temp on the end of it. We do that for each of the colors. Now what I've done here is I've said I want to now turn word features into all rows, but just looking at the blue and green column. Well, temporarily, I want to do a trick for you. I want to comment that one out and just show you what it produced before I limited the number of columns. In fact, I shouldn't have even done that. Let's just print it without reducing those. So I'll run it. Uh-oh, I need to run the cells above. So do those real quick. It may be that I need to go up even higher. Nope. So we see that, oh, well, now we get the original word features that we turned into a vertical NumPy matrix of 1 column. and we added the blue, green, and red. But if I bring back this line, all I'm doing is leaving those, the first column and the last column out, coming back -1 from this way, moving ahead to 1 this way. And now when I rerun it, I just get those. Okay, any questions at this point? And again, I promise to finally push some of this cool stuff to the repo for the class.
I did have a one, but I wanted to wait because I see you got pandas there, but I was, yeah, because you've done the one hot, you're now looking at pandas, so maybe I'll wait for until you've shown the pandas one because it might be answered already. So
very good. Yeah, but to remember your question, and I'll make sure I open the, oh, where do I get to the chat? I am not seeing, maybe, oh, there we go, good. Okay, Hugo, I now see your question. Guy, help me moderate the questions or you can answer them while I'm lecturing. Okay, to Jonathan's wish, we'll now go to the pandas example. Again, there's multiple ways to do things. We've got pure Python, we've got NumPy, we've got pandas, and sometimes we even have a TensorFlow routine we can use. Okay, now with pandas, we're doing the same thing. We're doing this, I'm just creating a fresh group of word features each time that are randomly sampled. And then I'm creating the colors set. We could have done this with NumPy or even with pandas too. But now I'm going to turn it into a NumPy array again, and I'm going to create a data frame. Now at this point, we can imagine that this data frame was loaded using pandas.read CSV. And we just received this data frame, and it had these colors that we need to run hot encode. But we still would need to say, oh, for DF colors, what were the unique values? So for color and colors, it's this simple. In fact, there may be a way to do this as one line. I didn't do it because I wanted to make sure this was extra clear. DF color, which is a new column I'm making, equals DF colors when it equals the color. So this will give me a group of zeros and ones. And again, now what will this do though? This part will give me trues and falses. So let's, for fun, let's comment out some lines and just see what we would have gotten if I had added those two lines. This is everything. Now, if I go on ahead and say, oh, but for each of those new columns you're creating, make it an integer. Well, false in Python, when you typecast it to integer, right now it's a Boolean. But if we typecast it to integer, look what happens. Ah, that's better, because that's what we were after. We wanted numbers, not text. And now, if I reduce, if I'm going to drop columns, what are the columns? The colors column and the last colors column, which would be, in our case, the red. So it's saying of the colors, get the name, the last name in this colors set, and drop that one too. So now when I rerun this, boom, I just get the blue and green. Again, for those of you that are just joining, when we're doing one hot encoding, there may be, let's say, 5 values that we're one hot encoding for. We only need n minus 1 of them. We only need 4 if we have 5. We only need 99 if we have 100. Okay, so that's basic one hot encoding. Now, the scikit-learn coders, very talented, wrote beautiful code. It's quite elaborate if you get in and start looking at the source code, but very well written, very good. be very instructional anytime you want to get into that. But to show the power of the scikit-learn pre-made classes for one-hot encoding, I'm now going to create two groups of colors, red, green, blue, cyan, magenta, yellow. I'm going to create word features and turn them into a NumPy array. And then I'm going to create more word features with the second group of more colors. And I'm going to turn those into a NumPy array. Then I'm going to stack them together. Again, this is the horizontal stack. There's also a vertical stack method, but this is the horizontal stack, and I'll call that all word features. And I'm putting together word features and more word features. And just for fun, let's do this. Let's do an intermediate print all, oh, thought it would show that. Word, there we go, finally. And then I'll go in and comment out these just so we can see some intermediate steps. So now you can see how we put both groups. We've got blue, red, and green occurring. We've got magenta, black, cyan, and yellow occurring here. Okay, I'll comment that out. Now we're going to use one-hot encoding. And I'm going to do the fit and the transform in two separate steps. So the first thing, I am just doing the fit of all word features. Now at this point, we can see the one-hot encoding instances, the class instance. We can look at the categories it found. So it's basically finding the unique values on its own. Let's look at that much. Oh, I might need to print that. So there you go. It found the unique values for the two groups, of course, which is important for our work. But we know we're going to one-hot encode. So just for our benefit, I know it's going to drop the first feature. That's one of the available parameters for the one-hot encoding class from sklearn. Okay, so I am going to use this list instantiation. Now let's go through this carefully. All I'm doing here is for each value in those categories, make it a list. Well, that's what we already did. Now what I want to do, in other words, put that to list, and that's why we could print that the way we did. By the way, I had to work through that carefully, just like you guys would have to do. But now I've got a double loop instantiation. You don't need to be confused by this. Remember, this would be like the way we would write this in Python. For sublist and categories, and then for E in each sublist, but only going from 1 to the n, meaning we are also going to drop the first of those groups it was giving us, put E here. So the way you'd write that as a for loop is this one first, and then colon return, then this one, colon return, and then append E to this category's array. But this is a way to save a lot of coding lines and still be relatively clear. So let's look at what that does for us. Well, we see we had two lists. Now all I did was turn it into a complete set of feature names not blocked off by list, and removing the very first one from each list. But you could have kept it as two lists and just dropped the first one from each list. That might have even been better. Okay, but here's the key step. Now we do the actual transform, and now we want to see the results of that transform. And again, since it's a special data type coming back from one-hot encoding, I just turn it into an array so we can print it better. And there we go. This, I did it this way so we could say, okay, this is for the green. This one is for the red. This one's for the cyan, magenta, and yellow. And again, on these two, when these two are 0, that means we have blue. When these 3 are 0, that means we have black, the first columns that we draw. Okay. Now, how could we do this in TensorFlow? TensorFlow is a little interesting. You have to use the indices of a known array, and then you can do that in TensorFlow. Now, some of you might ask, well, why would I use TensorFlow if it's going to do that to me? I could just use one of the 3 methods you showed me, or scikit-learn. It's only to just stay in the pipeline of tools for TensorFlow. But when you're using TensorFlow for a full pipeline development, there's oftentimes you can't use full pure TensorFlow, but that's okay. TensorFlow is a module for Python. We just maybe have to be a little more flexible the way we create our elements for the pipeline, our mechanisms. So let me see. Oh, these sessions are recorded, Tamiris. I want to PC to attend something. Okay.
So, sorry, Tom, can I ask the question now?
Yes,
you said the interject. So,
yeah.
So I've seen you go through the there are various ways, but also with the pandas, we can use the mapping feature, and we also have the dummies feature, which is less code. But when we use when we look at writing the actual Python code itself to one-hot encode or use another library, would one be chosen over the other due to performance, because they're all doing the same job? And yeah, that, is it a performance one to choose between?
Great question. For this type of stuff, most of the time, we're not looking at performance questions. However, I think the best approach, you get your first pipeline built with what you know best. And then once that development pipeline is running and you've put it in production, now you can go back and take the time to see, is the pipeline time scale, in other words, running the full pipeline all the way through to training the model and all of that. And now we have a pipeline we can put in production. Is that taking too long? And well, okay, I would like to make it faster, let's say, for example. So I go ahead and put that one in production, but now I find ways to identify the parts in the pipeline that are taking the longest. And I see what ways I can speed that part of it up. Then I go look at the next slowest part of the pipeline, investigate ways to speed that up. Makes sense, Jonathan?
Yep, thank you.
Yeah, and then, but you only do that.
Sorry, Tom.
Oh, you only do that if you see speed problems. Yes, Guy.
Yes, I have a comment here. It's about when we are conditioning the feature, at the end, it's about how many times this operation is repeated. That's why we are not, what Tom said in the beginning, we are not, let's say, think about the performance in the beginning, because the conditioning is, at the end, it's not one of the processes that consume a lot of resources. So this is the truth behind it. This is the first. The second, TensorFlow, PyTorch, they are promising a lot about when you are using it with a high performance for huge data sets and all of this, and all of the mechanisms or all of the steps. So yes, TensorFlow, they are promising with the best performance, but it's their promise. Okay, there is some process I tested by myself, and it's really great performance. They have great performance, but I cannot make their promise. It's their promise, not my promise.
Excellent. Very good. And thank you for asking that, Jonathan. Guy, help me with the questions and interrupt me if you need to about the questions in the chat. I'll keep going.
Okay, just also for 10 minutes. On the chat, I think Avinash, he asked question, I answered already, but for the sessions, Tamiris, the sessions are available on YouTube, all the sessions, and the current one, it's live on YouTube. So just we have to share with you the integrated MLI channel, YouTube channel. You can find all the mentoring sessions and all of the class sessions in 2 different playlists.
Yeah, exactly. Okay, thank you. Let's see, I need to make sure that, there we go. Okay, so for the TensorFlow, again, we're doing the same thing. We're creating, again, this is us creating the fake data. Now what I'm doing is this little trick. I'm going to convert those to indices of the colors. Now, in this case, I need to know what colors are going to be present ahead of time. Not a problem. I can create this unique set from what I loaded, and then I use the indices on that unique set. So colors dot index of W for W in word features. But again, if I loaded this and I hadn't created it fakely, I would need to get the unique values from this word features array, like we've done above. So then I print those word features so that we can inspect this. And then I print the indices, and you can see, okay, green's going to be 1, 1, blue is 2, and then finally red is 0. So now I just use TF, TensorFlow, dot one hot indices, and I get to tell it, oh, I know I have 3 up here, I only want 2. And which one will it drop? Well, it'll drop the first one. And in our case, that was the red. And so when we see 0, excuse me, it will drop the blue. And we have to figure this out sometimes. But you can see the third one was blue. And in fact, that's where they're both 0. Now, how do you figure out which one it's going to drop? It's dropping, in this case, the largest indice for TensorFlow. So again, it's just a little difference that we need to be aware of. And I found all of this out by looking at the TensorFlow documentation. A confession to all of you. Dad, Tom, Brother Tom, Dr. Ives, whatever you call me, I forget a lot of things. But I am a master reviewer. I know how to look things up fast, and Googling skills, web search skills, being able to look quickly through documentation or get to what you really need to learn from a Stack Overflow post or a Geek for Geeks article. All those are important skills. You'll get faster at it over time. I'm not saying I'm the fastest. I'm just saying I'm not painfully slow at it anymore. All right. Now, the next type of encoding we can do, like I said, is ordinal encoding. And so here we have this handmade quality list. And I just created an empty data frame. Can you do that? Yeah, no big deal. I created an empty data frame. And to that empty data frame, I said, okay, for the data frame, create a new column quality and set it equal to a series of the quality list. And boom, it worked. Awesome. Okay, now this, I love pandas. Now, usually it's, instead of look something up for 5 seconds and code it for a minute, with pandas, I often feel like it's look something up for a minute and code it in 1 second. So it's 4 seconds faster, but it's so elegant, it's usually worth it. That was an exaggeration, but now all I'm doing is this elegant thing. I've got my ordinals, which is a list of range of 1 to 8. What that's going to give me is 1 to 7. And then I say, I want a quality dictionary. I use this underscore capital D as a shorthand for my dictionaries. Use what you like. Use what's most clear. Main thing is I don't want to be wondering, oh, what was that variable name for? That wastes precious time. So just go ahead and use the longest variable names you want. So I'm going to make a dictionary out of zipping the quality list and the ordinals. Now this is cool. This actually creates an array of arrays, and each array in the array will have quality list and ordinals. But then I typecast that to a dictionary, and there's my dictionary right here in the output. Pretty cool, huh? But this is where it's beautiful. I can do a replace using that dictionary. And this is one of the powerful things with pandas. It's literally going to go through and say, when you see worst, like we had up here above, put a 1. Where you see poor, put a 2. And you can see it did it all right. So a quick, slick way to do ordinal encoding. Now, how would I do this with the ordinal encoder in scikit-learn? It's even easier. Here I have my fake word features again, so I've just regenerated them. And now I am going to use pure Python first. So again, I'm just getting my levels. Why did I do this? Forgive me. What was I doing here? Oh, I was just showing the method of creating the fake values, but we're going to recreate them here. Sorry for that confusion. So I'm getting the levels by that trick I've shown you already right here. Then I want the num levels. Well, how do I do that? Well, the length of levels, and then make that a range and turn it into a list. Why do I do this? Because I'm super lazy, but I'm trying to be constructively lazy, right? So, and in fact, for fun, well, y'all will trust me that this will create those levels like we had above. And then the keys. Again, the same trick. I'm zipping the levels and the num levels. These are the words, unique words. These are the unique levels, and I'm turning it into a dictionary. So with pure Python, yeah.
Tom?
Yes.
Yes, there's a question from Jonathan. When we encoding ordinals, should we start at 0 or 1? Can this affect the model?
I am going to answer your or question, Jonathan, the way I love to answer all or questions. Let me restate the question. When we're encoding ordinals, should we start at 0 or 1? Yes, we should start at 0 or 1. Okay, it really doesn't matter. And it may have been better if I started at 0, but I think it doesn't matter that much because truly, I still want to scale these, right? If let's say we've done min-max scaling of everything or something like that. Let's say we did a type of scaling where all the other features are between -1 and 1. Now the ordinal coding is from 1 to 7 or 0 to 6, whatever. Is that going to be a fair comparison when we go to linear or logistic regression and do the model weight? So we're still going to scale these. So yes, use 0 or 1 for clarity, but does it matter? Not if you scale them. Good question. I'm glad you asked it. So now I'm creating this empty array. And for quality in word features, I'm going to say num equals the keys. Again, the keys, I should have said D, but this is a dictionary. And for each quality in the word features, I'm finding the number for that word. And then I add it to encoded. I just append the number, but I'm doing it look at it. I'm doing it as a one value array. Why am I doing that? Just on a whim, but also because it'll be easy to convert it to a NumPy array directly. And then that way I could horizontally stack it to other NumPy arrays in my feature set. Okay, now if we use NumPy, it's all the same stuff, but here's the cool thing. Instead, let me see if I can get them both showing. I think I can. I think I can. I think I can. There we go. All right. Sorry, it's at the bottom here, but now I can say I've created a NumPy array of just zeros with the shape that I need. The shape was captured here for the word features. And I say, when word features, the column equals quality, then I set that to the keys dictionary quality. So basically, I'm correcting this one quality element at a time using, this is called a mask. And you can define these outside of here. I could have named this mask and like I said, mask equals this above the loop, and then just put it in here. But it would have to know what each of these were. And boom, it does it beautifully. Okay, and that's just the 3 in this case. If we use pandas, again, we're doing the same stuff again here and here, but look at this. Oh, wow. We just created a new data frame with a column of levels and word features, and we just replace it. Boom, like we showed above. So that's slick. But now if we use, and I know we already went through this, if we use sklearn's ordinal encoder, well, now I'm going to create more. I'm going to create 2 groups of features that have to have this done. So I've got word features for the first group on levels, and I turn that into a NumPy array. I've got more word features that I use on more, that I build from more levels, and I turn those into a NumPy array. And now I have all word features H stacked together between those 2. Well, now I'm just going to run, I'm going to instantiate the ordinal encoder. I'm going to fit with all word features. And then again, this is just some fancy different ways. Don't trouble yourself with this, that we're looking at the groupings, okay? And then here's where I do the actual magic, or scikit-learn does it for me. I ordinal encode through a transformation of text to numbers, all of those, and you can see the output, but I'll run it again just so you know I wasn't cheating. And there we go. I've got the first group, the second group, and now I've got the encoded features. Magic. Okay. We've got a few more minutes, so this will be fun. We can get into scaling, but let me stop and see. Oh, and Tamaris, more to the point, when your dad gets off his butt, I'll add all this to our course repo too. And then Jonathan will do his magical, helpful updates to let everyone know that I've actually done that. Okay, let's go over scaling features. And let me show you a cool thing. I love notebooks when they're used appropriately. I don't like them when they're used inappropriately. You don't use a notebook to build a pipeline, but you might use a notebook to teach a pipeline to others. So that's what we're doing here. So we started out here. You can see I love notebooks for when I create these text blocks, they create a table of contents for me, and I can just literally jump from one section to the other. Okay, now let's jump into some scaling for the little time we have left, and we'll continue with scaling next week. All right. And you know what? I'm going to go on down to this part. Okay, I'm just doing some helpful imports here first. So I'll go ahead and run that cell. Now, what is this? When I'm doing pure Python, I even avoid using math.exp. I like, no, I want to see it. So I go ahead and enter a good number of digits for E that I can raise to a certain power. So from now on, I'll just say E raised to some power. So we have that, and pi 2. And this was as many digits as I was willing to memorize for pi when I was an undergraduate engineer student. And I was never willing to memorize more digits than this. So there we have it. Then a very simple definition using, and just even pure Python makes this easy. I send in an array of data, I sum it, and I divide it by the number of elements of that array. And that is the mean. The standard deviation, a little more detail. I pass in the data. If I already know the mean, great, let's use it to save some computation time. And what type of standard deviation am I going to calculate? By the way, I've gotten some unfair negative votes on Stack Overflow that when you guys have the ability to vote, I would appreciate you going and helping me get more points on that answer, because some people were arm flailing because I used a small sample set in the example I was explaining, and they didn't like the numbers that were present. So it's a sample standard deviation. Come on, guys. But did they ever correct their votes? No. They just little dog mark on my Stack Overflow answer. Anyway, here's when, if sample is true, the n is going to be the number of points minus 1, just like for the sample standard deviation. Is my background noise okay, guys? Okay, thank you. But otherwise, we can use the population standard deviation. And so I make the default the population, because usually we're working with larger amounts of data. Now, if mu is not present, go ahead and calculate it. Otherwise, save the time. Now, sum of squared equals 0. Why am I doing that? Because I'm going to use this little trick in the for loop to add up all the square differences between the values and the average. And then finally, I just directly return the sum of those squares divided by n and the square root of that. That's my standard deviation. So I've run that. I'll just run it again. Well, oh, Tom, you're getting hardcore. You're coding your own probability distribution function. Yeah, it's not that hard. It's just math from a textbook, or from nowadays from Wikipedia, right? So what am I doing? I just broke the equation into 2 parts to make it a little more readable. Oh, look what I did. That was silly. I am on a call. And so this is just that first portion of a probability distribution calculation. And then here you can see that I've got, I'm going to multiply that same amount and set P equal to E to the -1/2 times each value that I send in. This is just a one value at a time thing. Subtract the mean, divide by the standard deviation, square that, multiply by a -1/2, take that whole quantity, raise it to E. That's just the probability distribution function. Now, the cumulative distribution function is adding all those tiny infinitesimal probabilities up. But how do we do that? With calculus. Oh, but you can't do that with analytical calculus. No one has ever figured out how to do it. They've done it in tables. Well, thanks to the magic of coding, we can integrate on the fly. So the range equals just, again, I want to integrate from left to right. Now, this is enough standard deviations to make sure I get the whole distribution, but, or essentially, not, I mean, again, engineering level, we don't have to be super exact. But I want to create an integer value here. I'm going to go from left to right, and then, well, the width, that's a panel width. I'm going underneath the probability distribution function curve. I'm adding up little tiny areas, and the width of those areas is only this wide. And so as I add those up, I'm going over that range that I either have default or send in, and I want to return that cumulative distribution value from this function. The way I'm doing that is for I in the range, and again, this width is going to make this range very large. I'm saying x left, because I'm starting at left, plus I times the width, that's my current x, and my current y, I send in that x, I get the probability of that point occurring, and then I add up that panel width. Again, I'm going to only go in steps of x at that width, but that's that small area under the curve, and we're adding up each of those panels. So again, if you, and I should put a picture of this. Let's see. I have that open somewhere. I want to show you Tina's excellent post, and we can maybe make this the stopping point. So Tina wrote this excellent blog post on the same of what we're doing here. Again, we're just trying to understand scaling deeper. So we're going under this curve, and we're adding up really narrow panels from here to as far as we want to go. But we can literally go from here to here if we want, or from the mean to over here. We're just adding up little panels under that curve. I think she might have, there we go. Cumulative distribution function, the same code here that I was just showing y'all. And we didn't actually, there we go. This is if we went from the extreme x left to the mean, or to 0, depending on what we're working with. And that's all we're doing, but all this is made up of very thin panels, okay? So now we want to be able to illustrate these too, so we create a histogram. Now, I only did this to control the bar widths. I'll let you guys study this on your own after I put it up on the repo. But now we've got all those functions and this way to visualize it. Now I want to create the fake data, and I'll make this the last thing, but we'll show some things with it too. I can do this with Python or with NumPy. You know what? I'm going to stop here because I don't want to rush this. But we'll use these two functions to actually create our fake data distributions. And here's us using the CDF. Excuse me. This was just a temporary one to create the what we showed above. I want to show you. Here's an example of what we can create with the function we're going to see above. And we'll look at our own written scalar techniques and compare those to scikit-learn. So you can see I was going from about 31 here to 43. And when we scale it, we're going from -3 to 3 using standard scalar. And we compare that to our PurePy method, to our NumPy method, and finally to scikit-learns, and we realize, hey, we got the concepts right because the difference in values between both of our routines and scikit-learns is 0. And then we'll go through the different types of scaling, min-max, standard scaling, min-max, max absolute, robust, and then some methods that can deal with extreme outliers, with data skew, and even something that's quite linear algebra-like, but can deal with practically anything. It's that robust. And with that, I'll see you guys and give you a little break and see you in mentoring. Thanks for being patient with all that.